Okay, as promised, we will look at how the work example that I've shared with you. And prior to that, there are some basic understanding or basic principles regarding um, liquid and vapor thermodynamics, especially when we're working for steam turbine. It's for water. Okay, and you'll be looking into some of the recap from chapter 7, and I think it's in the page excuse me, I think it's in page starting from page 335. So it's from page 335. So this is a revision on the meaning of the saturated line and how can you use them for your calculation. So the first part is the division of the diagram. So you have section 1. So this is section 1. So you have this section, and you have section 2, and you have section 3. And section 1 represents compressed liquid, and you can get all the values from table. Okay, values from table, and we'll get to the table later. And the same goes for section 2, where we also can get the values of entropy and enthalpy from the table, except that we have to introduce a new parameters, which is quality, because in section 2 is a mixture of liquid and vapor, and because it is a mixture, you have a portion of your working fluid to be in liquid form, and some of your working fluid to be in vapor form. So that's why you have to introduce this quality parameters. And then you have section 3, which is basically all gas, and you can also get the value from the table. Now there are many terms for the table. The one that I'm aware of from our textbook, it is referred to as saturated water table. You have for temperature only, and then you have for pressure only. So what this means is, for the temperature, that is when the temperature is constant, and for pressure is when the pressure is constant. So we'll look into how to use this table later. And we also have table A6 for superheated water, and these are all computed for a specific range of pressure. So simply said that it is for constant pressure process, and we'll look into how to use the table later on. But suffice to say, for Rankine cycle, it's not as straightforward as your normal gas turbine cycle, so you have to rely on empirical values of table. Empirical values obtained from experiment to calculate its efficiency and power output. Now let's look at, okay, since Rankine cycle uses water as its working fluid, the focus will be on the T and S diagram. So this is our T and S diagram, where you have saturated liquid line. Okay, this is the saturated liquid line, and then you have the saturated vapor line. Okay, and also you have a critical point. The critical point is not something that we will study yet, at least for thermodynamics too, but it is a very important concept, especially when designing a very high efficiency gas turbine, a very high efficiency steam turbine. But then again, it's not in our interest, not yet, at least just not yet. And then the table, yeah, so we have so this is the figure. The details of the figure is in page 336. Now let's have a look at a work example example 7.4 and discuss about entropy change during a constant pressure process, which is very important because the heat addition and heat removal in Rankine cycle is done as a constant pressure process. So the change of entropy is very important. Is a very important concept for us to consider. Now, a piston cylinder device initially contains 1.5 kg of liquid water at 150 kPa, and the temperature is given as 20 degrees C. The water is now heated at constant pressure by addition of 4000 kJ of heat. Determine the entropy change of the water during this process. Now, so the image of the process would be something like this. So you have a cylinder where you put a piston, where you close the lid with a piston and put some load to it, so as to create a pressure of 100 kPa. And now 150 kPa is a bit more than the atmospheric pressure. Our atmospheric pressure is about 100 kPa, so this is a bit more pressurized liquid, and the temperature originally starts at 20 degrees, so you have the temperature here as 20 degrees. Okay, the temperature at 20 degrees. And then as you heat up the water with our heat here, so the heat input is 4000 kJ. Okay, and the piston should move up so that it can maintain the pressure exerted on the liquid, on the water. Now at state 1, so this is the curve that we'll have. So the pressure is constant. It's a constant pressure. It's always 100 kPa, 100 kilopascal, and the curve is shown in this figure. So you have the curve here starting from S1, starting from point 1 up until point 2. So point 1, the entropy is S1, and point 2, the entropy is S2. Okay, no information is given regarding T2, but we can derive the T2 by calculating the entropy difference, which is what we are going to do. Now at state 1, the temperature is given 20 degrees, and our reference will be from table A4. Okay, so the textbook reference is on page 910. So we have enthalpy for the fluid, which is liquid in this case, and also we have the entropy value for the fluid in this state. So state 1, we are going to mark the enthalpy as H1 and the entropy as S1. Sorry. So S1 from the table, you can get the value. It's 83.915, and S1, or the entropy for the fluid, is 0.2965. So I'm missing a Kelvin here. Let me correct that. Okay. Now, these are the values that we will use to calculate the change of entropy in this work example. So okay, entropy change. All right. So note that we add heat to the fluid, and the heat is 4000 kJ. Okay, and remember from the first law of thermodynamics, which is basically an energy conservation equation. So energy is conserved, except that for the first law we are working on heat energy. So if we give an input of heat energy to a system, we will see the change in the internal energy, that is U, and plus some work that could be done. Of course, in this case we are not doing any work because we are maintaining the pressure. So we can directly calculate the Q in as a change of the enthalpy. Now we get the value of H1 from the table because that is our starting point. So we have our unknown to be H2. And in this case, because we know our mass, the mass of the fluid is 1.5 kilogram here. It's stated here. The mass of the fluid is 1.5 kilogram. So we can calculate directly the change of heat, or the input of the energy will affect the change of the enthalpy, and we can calculate the enthalpy from the energy equation. So we have 4,000 kilojoule. Remember to use the same order of equation. So we have H1 in the order of kilojoule, so the Q in, the heat addition, is also in the order of kilojoule. So we have to make sure that the order of magnitude for the energy is consistent. So H1, we got that earlier from the table, so that is 83.915, and the equation is here. So you have the equation here, and you finally, if you do the algebra, you can get H2 to be 2750.6. That's the value that I get, and also I believe the same value in the textbook. So textbook is on page 338. 338, yes. Now, so because we have our H2, then we can calculate our S2. Okay, so at state 2, again, we are looking at a constant pressure process. So P1 is equal to P2, but we have our H2 from the first law of thermodynamics to be 2750.6. Now, the textbook solution says to refer to table A6, and for your information, our textbook, the table A6, then have the values for P at 0.15 megapascal or at 150 megapascal. So you probably think that you can, just take a nearer table like 0.1 megapascal or the table from 100 kilopascal, and take another one from 0.2 megapascal or 200 kilopascal, and try to find a compromise for pressure at 0.15 megapascal or 150 pascal. But what I'm going to show you is that I'm going to show you that you cannot really do that, because in the end of the calculation, if you use the table for 0.1 megapascal, you end up with your entropy to be 7.5634 kilojoule per kilogram Kelvin. And if you use the 200 pascal to 200 kilopascal, you'll end up with your entropy to be 7.2356, which are both not the same as the solution given in the textbook. And the reason for that is you cannot just directly interpolate the value of entropy and enthalpy from a different pressure setting. That being said, I do have the correct table, and the correct table is published by, let me see, it's published by the correct table is published by, you have a table published by there's a standard table for this. Let me check again. Document. Yeah, I have the correct table, the precise one, published by published by NISTIR. So I think that is some standard institute. I've seen this table before during my student days, but I just couldn't remember the exact name of the institution. Well, anyway, the exact table is available, and I will share it to you. And don't worry about the kind of question that will come up for our exam. Yes, okay, that's the name of it. The exact table is available from National Institute of Standards and Technology. So this is the document. This document has been I mean, it's like forever. It's been there for a long time. They created these standards because the table for vapor and superheated water is all a standard. So they've done a very how do you say this? They have done a very great service to the engineering community by compiling the table and the data. So from the NIST data, I can get the calculation to be the same, about the same as textbook. So my calculation is 7.3673, and the textbook solution is 7.36. Let me confirm this again. 7.3674. Yes, that's correct. So that is the problem with this work example, just for your information. Now, the key takeaway here is the way that you use the table. So it's not really straightforward. You have to decide which tables that you can use, and this is something that I think I need to seriously address during our tutorial session. Next, so we have a constant pressure state change, so which is this example. Okay, entropy change during constant pressure process. And now the applicable part for our case, because we are doing Rankine cycle, will be the isentropic expansion. Okay, so isentropic expansion for the vapor, here the pressure is not constant, the pressure is dropping, but you have to find the physical quantities such as entropy, enthalpy for the fluid by using the table that gets its value from a constant pressure process. So that is there is a sort of lots of thinking that you need to do before you can decide which table to use. So we're going to look at the work example first. The example is on page, in textbook it's on page 339. So let me write that, P339. Okay, and we have an example of a steam entering a turbine at 1. So steam is entering turbine at 1 and exit at 2, and there's some work getting done. Now the basic concept will be the difference between enthalpy entering and enthalpy going out, which is I think you can it's very common sense. So you put energy, you put heat energy in, and there's some heat energy went out, and you are expecting to have some work done by the turbine. So it's basically a common sense if you put it that way. Now the input in this case is given pressure 1. The pressure entering the turbine is 5 megapascal, and the temperature is 450 degrees Celsius, and the output is 1.4 megapascal. And here we will need to use the saturated water table, the textbook, in our textbook that should be in table A6, to find the values of H1 and H2. Again, as a reminder, we are trying to find the value of H1 and H2, the enthalpy of the steam entering the turbine and the enthalpy of the steam exiting the turbine. So from table A6 that is on page 916, And if you sort at P equals 5 megapascal, so you have that T saturated temperature there. Simply put, if what the saturated temperature means, if you put water under a pressure, under environmental pressure of 5 megapascal, the boiling point, that is the saturation temperature, the boiling temperature will be 263.94 degrees Celsius. The simpler analogy would be when under 1 atmosphere, 1 atm, that is 100 kilopascal, the boiling temperature, the saturation temperature of water is 100 degrees Celsius. So at higher pressure, the saturation temperature or the boiling temperature will be higher. And from table A6, so you have P1 to be 5 megapascal, and the temperature of the steam entering turbine is 450 degrees C. So we have from our table, the reading of our H1 is 3317.2 kilojoule per kilogram, and S1 is 6.8210 kilojoule per kilogram Kelvin. And from table A6, we also have our P2. Okay, but here's the thing, here's the problem. Since the expansion is isentropic, so the entropy of the steam entering the turbine is equal to the entropy of the steam exiting the turbine. So because of this fact, we cannot use the table to get the value of S2. Okay, the value of S2, if you are not looking at the process, which is the expansion of the steam to produce work, you can directly read the values of H2 and S2. But that is not the case, because here we have an expansion and some work created from the expansion, and the process is isentropic. So we are assuming the entropy to be the same, to be constant during the whole process. So the value of S2, if we look at the table, okay, it should be equal to S1, which is 6.8210, and this value 6.8210 is somewhere between 6.7488 and 6.9553. So we have to estimate the value of S2, and this is where we will use linear interpolation, okay, to calculate the value of S2. The value of the enthalpy. Now, I've shown you earlier. Actually, I never talked about it, but if you look at the notes there, the one that's written in red ink, here you have Lagrange interpolation. So Lagrange interpolation is just a fancy name for normal interpolation, the most commonly used interpolation actually. And if you have just 2 points of value, so it's basically turned into linear interpolation. The thing that I prefer to use the Lagrange interpolation form is because it's a lot easier to show where the position of the interpolants moves. So here, if you can see here, if you have, if the value of H move closer to A, then you'll have this term to be HA minus HB divided by HA minus HB, which gives the value of S to be SA, while at the same time it will cancel out the value of SB, because HA minus HA becomes 0. So in a way, it's a much more intuitive and and a clear view of how to do interpolation. So let's go back to our problem. Okay, so we have linear interpolation, or to be exact, it's the same, Lagrange interpolation. And from our table, our value of S2 is in between S equals 6.7488 and 6.9553. So we have point A, point B, and the values are given as, for example, from table A6, okay, we are looking at SA to be 6.7488 and SB to be 6.9553, and the reading for the enthalpy is 2927.9 kilojoule per kilogram and 3040.9 kilojoule per kilogram. Since we have the exact table, so you can look at the table. The table is on page, you have the exact pressure table. So the table again is called, the table is table A6. You have a section for pressure equals 1.4 megapascal. Okay, so you can directly look at it and you can do your interpolation from there. Let's see. So the entropy is 6.8210. The pressure is 1.55. So you have somewhere to be around 6.7488 and 6.9553. Okay, so if you do the Lagrange interpolation, again, don't worry about, you should study the interpolation equation in a more detailed ways. You should put a little bit more attention to that, but I think I'll do I'll do a little bit more details regarding the interpolation technique during our tutorial session. So this is how we interpolate the enthalpy, and then if you do the math there, if you look at it, then after the interpolation you have the value of 2967.4 kilojoule per kilogram, and substituting the value of H1 and H2, you can finally get the work of your turbine, which in my case, I think it matches the value from the textbook. Let me have a look at it again. So 349.8, yes, so it matches the work from our work example. So the conclusion here is, for superheated water or vapor, using a table is a must, okay, because we cannot really have an exact equation to estimate the value of enthalpy and entropy for that for water and vapor. So it's empirical, but the table is in detail, so we can pretty much predict the behavior of water or vapor using the table. And two, heat addition and removal are constant pressure process, specifically for studying for using the table. For Rankine cycle, heat is added under a constant pressure, just like gas turbine, okay, where you have the combustion process occurred under constant pressure, and also the heat removal of the exhaust under constant pressure. And then this is important one, okay, enthalpy understanding is very critical. So you should be able to work between enthalpy and entropy if you really want to be able to understand how to estimate Rankine cycle efficiency. Now let's have a look at work example of Rankine cycle. The example is example 10.1, the simple ideal Rankine cycle. The textbook is on page 555. Let me see, 555, and it's actually the same as the one that I showed to you. I think it was our midterm test. Okay, we will do a midterm test based on this simple Rankine cycle. Okay, so there should be no surprise about that. Yes, it's page 555. Okay, so first thing first, if you look at the T and S diagram there, so you have 1 to 2, which is a process of compression. Okay, so that is isentropic. So it's a compression where you compress the fluid or the liquid. It's in liquid phase, so it's not gas. So you compress the liquid, and then there's a heat addition from 2 to 3. So this is where you need to be able to calculate the enthalpy at 2 and 3 by using the tables. And then you have expansion. Again, this is also the part where we revisited the idea of using the table to calculate work done by the turbine. So we have the steam entering the turbine at 3 megapascal, and the temperature is 350 degrees Celsius. And we also have the steam exiting the turbine, which is at state number 4, and the steam is condensed, meaning that it's being cooled and it's being in a liquid form again at pressure P4 of 75 kilopascal. So the way we approach this problem is to work on it state by state. So we analyze the first state and second state, third state, and fourth state, and then we came up with the enthalpy values for each point. So unlike the gas turbine, where we can skip the calculation of enthalpy and go straight to compression ratio or pressure ratio, we cannot really do that for steam turbine because of the phase change characteristic of the working fluid, which is liquid, water, and vapor. So state 1, so we are given the pressure from P4, which is 75 kilopascal, and that should also be the pressure for P1, because we are condensing the water to remove the heat, so the water again becomes in a liquid state. It becomes liquid phase. So P1 is in liquid, so we have H1 and V1 that we can refer to the value we can refer to from table A5. So the table is saturated water and pressure table. Now at P1 equals 75 kilopascal, the enthalpy H1 is equal to HF. F stands for fluid, meaning it's in a form of fluid, or to be exact, it's in form of liquid. Okay, so it's in a form of liquid. So the enthalpy is 384.44 kilojoule per kilogram. And of course, we also can find the volume of the liquid at this pressure, which is 0.001037 cubic meter per kilogram. Next, at state 2, so state 2 is basically where we compress the liquid, and before entering the boiler, the pressure again remember from our first recap, the whole process for Rankine cycle involves a constant pressure heat addition and a constant pressure heat removal. So from state 2, we are talking about a constant pressure heat removal, heat addition at the starting point. So pressure at 2 should equal pressure at 3, which is a 3 megapascal, and we are adding heat to the process. Now, since you are going from 1 to 2, the pressure is 3 megapascal, but the compression is isentropic, meaning S1 is equal to S2. So we have to we can only calculate the enthalpy indirectly. So the first thing that we need to do, although the work of the pump is in the form of H2 minus H1, but we cannot really find H2 because S1 is equal to S2. We cannot directly use our table. So the other way, so we have to look at the work done by the pump first. And in this case, because the volume of the liquid water being nearly incompressible, so the volume of V1 should remain about constant. So the work done by the pump should be the difference between the intake and the output, input and the output pressure. So the input pressure P1 is 75 kilopascal. The output pressure is 3 megapascal. So if you calculate that, so you will have our work done by the pump. Okay, so you have the volume V1F here, and the work done by the pump. Remember to use the same order of magnitude to calculate the enthalpy and entropy. So here we get the work of the pump is 3.03 kilojoule per kilogram, and from there we can calculate H2, which is from the first equation. From this equation, we can calculate the work of the pump. We can calculate the work of the pump from here, and then we can calculate H2 by using the work of the pump plus the enthalpy 1 H1. So we have work done by the pump here, which is 387.47 kilojoule per kilogram. Next, note that we will use H2 to calculate our input heat. And on state 3, again, pressure at P3 is equal to 3 megapascal, which is also equal at P2. And the input temperature for the turbine, for the turbine inlet is 350 degrees Celsius, which is given. And here we can use table A6 on page 915 to get the value of H3 and S3. So we already have our H3 and also our S3. And finally, at step 4, this is the part where it gets a bit tricky, because state 4 is a mixture of liquid and vapor. So we have to consider the purity, it's quality actually, the quality parameter, that is X. And we also know from the input and output of the steam that pressure 4 is equal to pressure 1. And because it is an isentropic expansion, so the entropy S3 is equal to entropy S4. And from the quality parameter, so we are going to denote it as X4. We can calculate it from entropy of the fluid and entropy of the fluid mixed with gas. The G here stands for gas. So you can get this SF and SFG reading from table A5. And table A5 is the reading for entropy at constant pressure. So the reading for SF at 75 kilopascal is 1.2132 kilojoule per kilogram Kelvin, and SFG at 75 kilopascal, the value is 6.2426 kilojoule per kilogram Kelvin. So we can deduce from that our X. So our x4 is S3, which is the value of this isentropic, the value of S3. Okay, we already got our value S3 from state number 3, that is 6.745. And if you do the algebra, if you do the math, we can get our x4 to be 0.8861, which is actually, which means it's a percentage of let's see, it's a percentage of fluid to gas. So simply put, at this stage, there are more gases, the percentage of gas is bigger than the percentage of fluid. Okay, at that point, at S4. So because we now have the ratio, which is x4, then we can calculate H4 using the same concept. So our x4 is the same, it's the same applied to HF and HFG. HF and HFG can also be taken from table A5, the same table where we get our entropy. Okay, it's just the value is just side by side. So our HF at 75 kilopascal is 348.44, which is the same as H1, our starting point, and HFG at P equals 75 kilopascal is 2278.0 kilojoule per kilogram. And the ratio, the quality, x4 is 0.8861. So if you do the math, if you do the calculation, we'll end up with H4 to be 2403.0 kilojoule per kilogram. Note that now we have our H4, we also have our H3, we also have our H2 here, and we also have our H1. H1 is actually here. So we can calculate the input energy, the heat input, which is Q in, and also the heat output. So the input heat addition is H3 minus H2, and the output heat, the waste heat, is H4 minus H1. And substituting all the values, we end up with the final conclusion, the final calculation of the efficiency of the cycle to be 26%. Q in, Q out. Okay. Remember H4, H3, and finally we have 26.02%. So this work example will be our format for the mid-semester test. No, not for the mid-semester test. It's for our final test. Okay, and as I promised you, we will only do the original cycle because it's the fundamental. So we really need to do that. We really need to get good at that, and we'll probably choose between let's see, doing the reheat cycle and the regenerative cycle. We will consider the two of them, okay, to come to be our final question. Of course, I would prefer the simpler one, and I think we should discuss on which one we should use for our final examination. And because of the time limit of the final examination, I honestly would prefer that you don't have to use the table that often. So we will think about it later during our tutorial. So that's it for this video. Thank you for listening, and hope you enjoy the content.